First of all, I would like to thank the organizer for giving me this opportunity to talk about my subject. So my talk, the title of my talk is Caustics of World Sheets in Lorentz-Minkowski 3 space. And then this is contents, but I don't mention much here. Then, so what is a world sheet? Then it is a time-like submanifold in a Lorentz manifold, which is foliated by a codimension 1 space-like submanifold. And each leaf is called a momentary space. Then I will explain the detail in the later, but why we consider such a special submanifold in the Lorentz manifold. Then there are several motivations. Then one of the motivations is the so-called brain world scenario. It's so it is a theory in some theoretical physics. So then they say that our universe is a 4-dimensional Lorentz space in higher dimensional Lorentzian manifold. And then so our universe can be considered as a world sheet. And the second motivation is we have no notions of the time constant in the relativity theory. Because if some observer say this is 1 o'clock, but a different observer can say this is 2 o'clock. So we cannot fix the time in the relativity theory. And also, for example, if we consider the surface of the body, for example, the surface of my body, because I'm moving, but even if I fix my body, you look, it's fixed, but our Earth is moving, and also the galaxy also moving. So and then so nothing fixed in some coordinates. So there in relativity theory, everything that is moving. So it depends on time. So it is. So for example, if we have some surface, so it consists. It is a 3-dimensional world sheet in 4-dimensional some Lorentz space. Okay, and also there is a theory of superstring theory it is related to this brain world scenario, but they consider the D-brain. D-brain is also world sheet in the higher dimensional Lorentz space. Of course, if we consider one-parameter families of some manifold in Euclidean space, it can be considered as a world sheet in higher dimensional 4-dimensional Minkowski space. Okay, so, but here, of course, we have general theory, but for convenience, we only consider 2-dimensional world sheets in Lorentz-Minkowski 3 space. For it is easier to understand what we consider. But of course, we have a similar result for higher dimensional cases and for other Lorentzian space forms. And higher dimension means higher. This is a codimension one case, but higher dimension means higher codimension. But this is rather complicated. I talked several times about this, but people didn't understand. So now I decided to explain 2-dimensional in three-dimensional Lorentz-Minkowski space. But Lorentz-Minkowski space has no gravity. But this is a just a very simple toy model for such a general case. And then we start. We now start the Euclidean case. What is the caustics? I will explain. So maybe everybody knows this notion. So firstly, I explain the plane curve case. So for example, if we have a plane curve like this ellipse, then we consider parallels. This just it is a normal direction. We have distance, same distance. Then we consider family of parallels. Then some distance we have singularities of such parallels. Then the trajectory of this family of singularities forms this I don't know, four cusps singular curve. This is a notion of evolute of the ellipse. But also there are another interpretation of the evolute. That if we consider the normal family of normal lines from this ellipse, then we consider the envelope of such normal lines. Then we have this envelope. This is exactly the same as this previous notion of evolutes. So then it corresponding to this is a kind of wave front. So the ray considered as a wave or particles. Then so if we consider, but this is rather classical optics. Then, but if we consider particles, then we have this kind of envelope. Then but this envelope, this evolute can be given by the following way. Then if we consider gamma as a unit speed plane curve, then we have curvature. This is differential geometry. So then NS is a unit normal of this curve. So it's this, for example, this direction. Then the evolute is given as this form. So this from the distance is just 1 divided by curvature. It is easy to calculate this one, but this is a representation by using this curvature of evolute. Okay, so, but for space case, we have surface. It's similar to the plane curve case. Then if we have a embedding that is a surface, and then we have the unit normal vector field along M, it's then as everybody knows that elementary differential geometry course, then there is a principal curvatures of M at each point. Then in general, there are two, but sometimes it's one. Then, but the evolute of, or the focal set of the surface in three-dimensional space is given as follows. So here, this is exactly the same as the previous evolute of curves. This I just changed the here is 1 divided by the principal curvature. Then it is known that maybe Ian Portas was the first person to give this classification of the generic evolute has singular points, And then generic classification of such singular point is two. We have 4 types of singularities. The first one is cuspidal edge. Second one is swallowtail. The third one is pyramid. And the fourth one is path. Then these 2 cases at this point, then this curvature coincide. So that's the umbilic point here. Then, but how can we classify this evolutes? Then we apply the singularity theory of the unfolding of functions. So here we consider distance squared function. This is given by just distance squared. Then we have the notion of the bifurcation set. That is a first derivative and the determinant of Hessian vanishes at some point, then on some parameter space. Then we can show that this bifurcation set is equal to the evolute of M. Then we apply this the classification theory of unfolding. Then so the Tom's list of the 7 catastrophe theory. Then we have this classification. Then, but the evolute can be considered as a caustic in the symplectic framework. Then I don't mention the detail here, but caustics in general is defined as a set of critical value of the projection restricted onto a Lagrange submanifold L. So we have this projection. L is a Lagrangian submanifold in the cotangent bundle, and then projection mapping L to this base space, and then critical value set is the caustics in general. Then so we can show that the evolute is a caustics. And the typical example of the caustics, it is the caustic of rays reflected by a mirror. This is a picture of the caustics. Then here there is some mirror. Then I took this one in the Newcastle's museum in here when I visited Farid. Then this is very beautiful picture. Then, but the caustic, in this case, the ray is a straight line, and we have this envelope. Like it's my first example of the evolute. Like then this is a story in the Euclidean case. What I think what is a caustic, everybody understood. I think, I hope. And then now we consider Lorentz-Minkowski space, 3 space. Then, so Lorentz-Minkowski space is a 3-dimensional Cartesian space, and with this pseudo-scalar product. This here for x and y, we have x0, x1, x2, then minus x0, y0 plus x1, y1 plus xy2. So it is minus plus plus type scalar product. And then the important things is there is 3 types of the vectors. Then the non-zero vector is called the space-like if this is positive, and right-like if it is 0, and time-like if it is negative. Then we have the pseudospheres in 3-dimensional Minkowski space. Then we have, because this is the radius is imaginary. It's a minus square. And this is radius 0. This is radius is real. So then I can draw the picture here because I use then we have this x1, x0, x1, x2 space. Then in this case, x0 equals the origin. So LC is something like this. This is a cone. This is so right cone. And this is a hyperbolic space. In hyperbolic space, this is LC0. And this is these are hyperbolic space. Oh no, this is 2. 2, 0, minus 1. This 1. And third one is so the Dositta space is S2, 1. No, these are S3 is not 3, it's 2. And then we have 3 kind of spheres in the Minkowski space. Then we consider surface in Minkowski space. Okay, so then, but because our subject is world sheet, so world sheet is a time-like surface. So then we only consider time-like embedding. So time-like embedding means that something like this, the surface. So the tangent space at each point, the TPM is a Lorentzian plane. Then, of course, we can consider general surface, but here we only consider time-like surface. So general surface case, the surface can separated into 3 parts: the time-like part, space-like part, and the light-like part. Then the evolute, for example, Farid's result on the evolute of general surface cases. There are so many detailed investigation by Farid-Tari. But here we only consider time-like case. And then we have the space-like unit pseudo-normal vector field. So we have, at each point, we have this space-like unit normal vector field. Space-like means that NN is positive 1, so then it's outside of the right cone. It's directed outside. Then, by using the image of N is located on this Dositta space, and then by using this pseudo-normal vector field as Gauss map in Euclidean case, then we can define the curvature. That is this is the Weingarten formula for this space-like unit vector field. That we have this. I don't mention the detail here, but some kind of representation of this derivative of n. Then, by using this matrix, then we have the principal curvatures. The eigenvalues of this 2x2 matrix. But here, it's different from the Euclidean case, because Euclidean case, it's metric on the surface is Riemannian. So it always the principal eigenvalues are real values. But here, sometimes it's complex values. So it's a Lorentzian metric. So it means that the principal curvature not always exist. In real complex value cases, we have no principal curvature. Then, similar to Euclidean case, we have Lorentzian evolute of M. So it's exactly the same formula, but just if the principal curvature exists. Then but this is almost same as Euclidean evolute. So we have the generic classification of singularity of this Lorentzian evolute is the same as the Euclidean case. Maybe, I don't know, Farid Tari mentioned his paper. Then, so the cuspidal ray, swallowtail, and pyramid, and path. Okay? Then, of course, in this case, how can we classify this singularity? Then we have the Lorentz distance square function. This is Lorentz pseudoscalar product, Minkowski pseudo. Instead of the canonical scalar product, we use this Lorentz-Minkowski product, scalar product. Then also we can show that this bifurcation diagram, bifurcation set is equal to evolute. Then we can apply the singularity theory of unfoldings to this case. But we consider the geometric meaning of the evolute. Then so if the curvature, two principal curvature coincide, that means that totally umbilic case. Totally umbilic case, it is equivalent to that the evolute is a point. And then in this case, it's also equivalent to the condition that surface is located in some Doshita. Here is S21 Doshita space. But center of the Doshita space is given by the evolute. This point, and radius is 1 divided by curvature. So Euclidean case, the singularity of evolute estimates the contact with the sphere, because Euclidean case, the totally umbilic case, is the surface is part of a sphere. But here, the totally umbilic case is the surface is part of the Doshita space. So it means that the Doshita space is a model of this time-like surface. Of course, similar to Euclidean case, it can be also considered as a critical value set of the projection of the Lagrangian submanifold in cotangent bundle. But this case, normal line is this, directed by this, because this is time-like embedding, so then n is a space-like. So normal lines are space-like lines. These cannot be considered as rays, because in relativity theory, the speed of particle cannot exceed the speed of ray. So then this is not a ray. The ray always tangent to the light cone. So the Lorentzian evolute is not a caustic in physics. So it means that this notion is just a mathematical notion. It's not physics. The notion is physics. Okay, so, but we consider world sheet now. Okay, so then world sheet is, I mentioned in the introduction that time-like surface with extra condition. This is Fouriered by space-like codimension submanifold, one submanifold. So it is so we have this foliation, codimension one foliation. Then so we consider local situation. So we consider gamma time-like embedding from I times j. The ij are open intervals. Then so each fixed t, the element j, we have the each leaf. Then it is denoted by gamma t s for fixed t. Then we assume, in this case, this is a curve, space-like curve. So we consider arc length parameter. Then W is the image, and ST is the image of this gamma t I for each t. Then we have this foliation on W. Then under this situation, we say that WS what is a world sheet. If the W is time-orientable, time-like, and each leaf is space-like, then time-orientable means that there exists time-like vector field on this surface. Then, of course, this case is local case. Then always we have this time-like vector field. Then we choose either as a future. Then, of course, we can choose either as a past, but doesn't matter. We like the future is upper. So then each leaf is called a momentary space, and then we consider some differential geometry of this world sheet. Then we have, of course, this is a time-like surface, and we have the unit pseudo-normal vector field along W. It's the same as the previous one. We have this N at each point. And then we consider the unit space-like tangent vector of this each momentary space, momentary curve. It's just a derivative of gamma. With gamma prime, we have this T. And then we consider the pseudo-exterior product of NT. Then it is denoted by B. Then we have B. Then that pseudo-exterior product is just analogous notion to the ordinary exterior production in Euclidean. This is Lorentzian version. Then we choose the orientation of this each momentary space such that this B is the future upper direction. Then we have this three pseudo-orthonormal, this pseudo-orthonormal frame along W. Then this is nothing but a Lorentzian Darboux frame of each curve, each momentary space. Then we have the natural equation. Just we don't consider the derivative of time t. Just we consider space parameter. And then we have these three kind of natural equation. Then here, kappa g is given by this. It is geodesic curvature of this each momentary space. And kappa n is a normal curvature of each momentary space. And tau g is a geodesic torsion of this momentary space. Then this is a basic framework. And then, again, we consider the distance squared, Lorentz distance squared function, d. Then if we consider just same as the previous calculation, we have Lorentzian evolute. But here, for any t0, any time t0, we fix t0. So we have this restriction of the Lorentz distance squared function. And then we consider the discriminant set of such Lorentzian distance squared function. Then just by the calculation, simple calculation by using this natural equation, and then we have the zeroth derivative and the first derivative equal to 0, if and only if there exists a real number u, and x is given by gamma st0 plus u times b plus minus n. We can easily show this. Then, but here, because b is time-like unit vector, and n is a space-like unit vector, and then pseudo-orthogonal each other. So then the summation of n plus b plus n is right-like. This is b plus n. And b minus n also right-like. So this is for each fixed S, this is a line directed by right-like vectors. So we have right-like lines here for fixed. Then this we consider the surface, ruled surface defined by this S parameterized by S and U. Then each ruling is a right-like. So we call this is a right sheet. Then so if we consider consider this two right-like lines, we have some, I don't know how to say. Two ruled surfaces along this ST0. Then, but each direction is right-like. Then we call this is as a right sheet along ST0. Then, of course, this right sheet has singularities. Then we consider such singularities. Then for the point on this right sheet, then the second derivative with respect to S is equal to 0. If and only if, then we can show this kappa g plus minus kappa n is not equal to 0. And U is kappa g plus minus kappa n, 1 divided by kappa g plus minus kappa n. It's similar to Euclidean evolute, but instead of kappa, we use kappa g plus minus kappa n. Then, it means that the singularities of this right seat is just a substitute of U of this condition. Then we now define the right-like focal curve along this ST0 by just substituting U into this right seat. Then we have this right-like focal curve along each momentary space. Then, then we can show that the generic right-like focal curve is locally ephemeral to 2, 3, 4 cusps. That's the t squared 3, t star, t power of 4. Then, so now, the purpose of my research is what these two physicists construct then to understand these two papers of Rafael Bosso and Lisa Randall. Then they consider the holographic principle, then holographic domains. Then what they considered, I tried to understand these papers. Then especially, I didn't understand their calculation, but especially this picture is very interesting. Then so this picture, then this is a very simplest case of our situation. Then we have this circle, space-like circle, instead of ST. Then the right seat is two right cone here. This kind of skirt. Then we have two right cones. Then they say that so right cone. Then here we have just the focal set in the previous definition. Then they call this a caustic. Then, but of course, this is this circle is moving depending on time t. Then in this case, they consider the cylinder just a very simple case. Then so the trajectory of this focal point is just a line to x0, parallel to x0. Then the idea of Bosso and Randall is a holographic domain is a region where the right seat sweeps out until caustics. So this means that this is the right seat, then it sweeps out, but until caustics. So the holographic domain, if we remove the x0 axis, then we have holographic domain. Then why we consider this such a domain? Then because this case, our case is simplest toy model, but if we have gravity, then gravity propagates as a speed of ray. So this ray is gravity. So everything reach, but any information from the past we get inside of this holographic domain. So but I don't know the detail of the holographic principle. But for example, this caustics is a boundary of the universe. So it means that there are now in physics there are many theory of multiverse model. Then this is one of the multiverse model. So there exist several universe, not the universe, multiverse. Then the boundary is given by this caustics. So then if we classify this the shape of this caustics, this is the boundary of our universe. Then outside of our universe, we have no information. Then, so it is a kind of horizon. Then, of course, if ray is real ray, then this caustics explain the boundary of event horizon. That's so. Then, if we cut some space-like surface that is an observer, then we can see the shape of black holes. And also, there are many other cases. Then, from mathematical viewpoint, then we understand that the caustics is the trajectory of the focal point. Then we define the notion of caustics of the world seat. Then the caustic of the world seat in the sense of Bose and Landau, given by the union of the right-like focal set. We have two branches, C plus minus. We call this BR caustic of WS. Then, of course, I am a mathematician, so then I'm interested in the geometric meaning of these caustics. And then for the point on the caustic, then the third derivative of this distance squared function is equal to 0 if and only if this quantity is equal to 0. So then we now define a new invariant of W given by this, the same as this part. Then we can show this new invariant is constant, sigma plus minus is constantly equal to 0. If and only if this focal point is constant, then this momentary space belongs to right cone. Then so that it means that if we move T, then the family of right cone, momentary space belongs to family of right cone. Then this means that the model, this is a model surface. Right cone is a model surface of this each momentary space. Then, of course, we are interested in singularities. Then, so that this focal set is locally diffeomorphic to cuspidal edge, and only if this invariant is not equal to 0, and it's diffeomorphic to the swallowtail, this invariant equals 0, and the derivative with respect to S is not equal to 0. This is a classification of the focal set of along the momentary space. But also we can show that there exists a Lagrangian submanifold in this cotangent bundle, such that this it's a union of C plus and C minus that BR caustics is a set of critical value of this projection. It's of this Lagrangian map. So, but this is a similar property to the evolute in the ordinary caustics of time-like surface or a surface in Euclidean space. But however, the classification of singularities are different. Then, so for generic world seat, the BR caustic are locally diffeomorphic to the cuspidal edge, only cuspidal edge or the swallowtail at singular point. So then the pyramid and path never appeared as the BR caustics of the world sheet, even non-generic. So because so it's a little bit different from the ordinary caustics. Then, of course, this case is lowest dimension case. So higher dimension case, then if we consider hypersurface, the world hypersheet case is the construction is rather easier because codimension 2, we have 2 directions. But higher codimension case, it's we don't have this 2 direction, just infinitely many direction as a normal. So then we consider at each point we have right cone, a kind of right cone. It's not exactly the same as a part of right cone. Then the right cone moving along this momentary space. Then the envelope of such right family of right cone gives some right sheet, and then the critical value set is also as BR constant. But such construction I tried to explain several times, but people couldn't understand. But this case is much simpler, and then I finish now.
Any questions? I'm going, because there is...
Not necessary.
No, it is, because there is...
The film, okay. So the question is, okay, you have the theory of prohibitions, right? There are some singularities, they never appear right in this situation. What is the reason? Why don't they appear? How do you, do you have some motivation for these prohibitions?
What do you mean?
You have like D4 singularity doesn't appear. Why?
Why?
Because the slide before, you have either cuspid ledge or swallowtail. So you don't have person.
This?
Yes. Why you don't have a person pyramid?
Yeah, because this is a family, one parameter family
exactly.
of the curves. So then so we have some so regularity depending on the time t. Then this path and pyramid codimension 2, but maybe so. Then this is a crank 1 singularity only.
Okay, but in general, can you give some sort of criteria of the singularities who never appear?
Yeah, because this is only
no, this, but everything.
Yeah, but crank 1. This is a crank 2. So then we don't have such in general.
More questions? Right. Well, let's thank the speaker.